All right, ladies and gentlemen, yet again, we're going to be talking about systems of linear equations. We're going to have one more lesson about this later on. But for now, let's recap. System of linear equations, remember, two or more linear equations where each of the equations has the same x value and the same y value. In the last presentation, we talked about graphing these equations. So when we graph them, remember, if it had one point in common, the graphs intersected at that one point. The x value of the point and the y value of the point represented the solution to both equations. Okay, so substitution method. Again, this is just a recap of what we talked about. Instead of either doing trial and error or graphing, we're going to use something called the substitution method, which involves solving equations. Okay, so just like we were doing before we started this lesson when we were reviewing solving for x, we're going to do something similar to that where we have to manipulate the equations to do the substitution method to solve for x and y. Okay, so in this case, we're going to be solving one equation for one of the variables and then substituting the new form of the equation into the other equation for the solved variable. We're going to talk more about what that means in a bit. So if that sounds a little too wordy, don't worry about it. It basically means that we have to manipulate one of the equations to get something in common so that we can substitute what that common thread is into the other equation. Okay, and again, I'm going to show you an example of this. So if it's still hazy, don't worry about it. So let's do a quick example that should be a review from last semester. Let's say that Internet Company 1, okay, we're thinking about buying internet. Internet Company 1, the cost of internet is equal to $20 a month plus a $35 activation fee. The cost of Internet Company 2 is equal to $15 a month plus a $75 activation fee. Now my question to you is, when are the costs going to be the same? Okay, when are the costs going to be the same? Well, let's think about what this question's asking. If the costs are the same, this variable of c represents cost, and this variable of c also represents cost. If the costs are the same, another word for same is equal, right? So I'm wondering when C1 is equal to C2. Well, if I write out C1 is equal to C2, does that really help me? No, it doesn't, right? I have nothing to solve for. But if I say C1 equals C2, what else do I know? I know that C1 is the same thing as not just C2, but it's also the same thing as 20m plus 35. And C2 isn't just the same thing as C1, it's also equal to 15m plus 75. So if these c's are the same, then these two right sides of the equation should also be equal to each other. So let's think about that. If C1 is equal to C2, and we know that C1 is equal to 20m plus 35, and C2 is equal to 15m plus 75, then that means, I'm not sure why I put another comma here, that means that 20m plus 35 is equal to 15m plus 75. I'm going to pause so that you can let that sink in just in case it went a little too fast. So again, if my c's are the same, which is the left side of my equation, this variable, then what they're equal to, which is the 20m plus 35 and the 15m plus 75, should also be the same or equal. So now that we have this equation, guess what we're going to do? We're going to solve it. Okay, we can actually solve for this. We can't solve anything here. There's nothing to solve for. This we can solve. So let's do that on the next slide. Weird. So my original equation is 20m plus 35 equals 15m plus 75. So first thing I'm going to do is I'm going to subtract 15m from both sides. I'm going to get 5m plus 35 equals 75. Now what I want to do is because remember, my goal is to get the variable by itself. I'm going to get rid of this 35. How do I get rid of it? I'm going to subtract it because it says plus 35. So to get rid of a positive 35, you subtract 35 from both sides. I get 5m equals 40. And since this is multiplication, to undo that, I'm going to do division, m equals 8. Now, if m equals 8, I can figure out when these two are going to be the same. I know that the cost is the same at month 10. How much is the cost at month 10? Well, if I plug in 8 times 20, I get 160. 160 plus 35 is 195. Same thing here. 15 times 8 gives me 120, and 120 plus 75 also gives me 195. Okay? Since 195 equals 195, my coordinate's actually going to be 10, comma, 195. So the cost is the same at month 10. So when m equals 10, the cost, which is c, is equal to 235 for both equations. The other thing I need you to know is, remember, if we're solving for linear equations or systems of equations, we need both x and y. So we need both values of both variables. In this case, we had m and we had c. Well, we figured out m was 8. We figured c out by plugging 8 in for m, and we got 235 in both equations. That's another way we're going to check. Because if I plug in 8 here and I get 195, but let's say I plugged in 8 here and I got 200, I did something wrong. Okay, I'd have to go back and check my work. In this case, it worked out, so I don't have to go back and fix anything. My answer is just 10 and 235. I'm done. Weird. So let's look at an example. And I'm going to do this as a model. This is a little bit different. In the previous example, we had one variable on each side. We had c, so we were able to substitute what the values of c with everything that had the m in it. This one's going to be a little bit different, so please, please, please pay attention. Okay? There's a lot of detail here. Solve the following system using the substitution method. Well, my system is 3x minus y equals 6, and negative 4x plus 2y equals negative 8. So when I'm using the substitution method, remember, if I substitute something, that means I'm going to take something from here, and I'm going to plug it in here. Okay, that's what substituting means. So I'm going to look for something that is in common. Is there any way I can manipulate either one of these equations so that I have something in common? And when I say something in common, I mean either an x term or a y term. Okay, I always have to get an x term or a y term when I'm doing this. Well, the one thing I can see right now is there's a y right here. So if you remember from the last lesson, we figured out how to get y equals mx plus b equations by manipulating this problem. We're going to do the same thing here. And I'm going to show you how this is going to work when we substitute right after. So let's say we have the equation 3x minus y equals 6. Again, I want to get the y by itself. So when I get y by itself, first thing I'm going to do is I'm going to get rid of that 3x on both sides. So I'm going to subtract 3x. If I subtract 3x from the left side, these cancel out. Subtract 3x from the right side, I just have negative 3x. Because I can't subtract it from 6, I have to subtract it from 0. I get negative 3x plus 6 equals negative y. Now how do I get rid of that negative y? This negative symbol, I need to keep the y, get rid of the negative. To make this positive, I can either multiply or divide, doesn't matter which one I do, by negative 1. I'm going to multiply in this case. Negative 1 times y, or times negative y gives me positive y. Negative 1 times negative 3x gives me positive 3x. Plus 6 times negative 1 gives me minus 6. Okay? So now, this first equation, I didn't make a new equation. I used the same equation, I just manipulated it. Okay? This 3x minus y equals 6 is technically the same thing as y equals 3x plus 6. It's just written in a different way, okay? They mean the same exact thing. Nothing is really different. They just look different. Now, see how it says y equals 3x minus 6? What this is saying to you now is, anywhere that you see a y, I want you to remove the y and plug in a 3x minus 6 in this equation. Okay, so anywhere that I see a y in the second equation, the one that we didn't change, we're going to take this value of 3x minus 6 and we're going to substitute it or plug it in for y. So if I look closely, here I have negative 4x. I'm not going to change anything here. Then I have plus 2 times y. Well, we just said that y is the same thing as 3x minus 6. So if y is the same thing as 3x minus 6, I'm actually going to take out this y, and I'm going to plug in 3x minus 6. Okay? So again, we're going to substitute this value of 3x minus 6 for y in the second equation. Here's what it looks like. Here's what happens when we substitute it in. And the reason why I put it in parentheses is because if you don't put this in parentheses, that means you're only doubling the 3x. Okay, if I did not put parentheses here, it would just say 2 times 3x, and then you'd just be subtracting 6. But since this whole thing is y, and you're doubling y in the equation, we need to double this entire thing, okay? Because remember, this entire thing is y, not just the 3x, not just the minus 6, the entire line of 3x minus 6 is the same thing as y. So if we're doubling y, we're doubling this whole thing. Okay, so in this case, if I see parentheses, parentheses means distribute, so I'm going to do that. What do you notice? We don't have two variables anymore. When I had two variables, I couldn't solve for anything, right? Now everything's in terms of x. Since everything's in terms of x, I can solve for x. So let's finish this. We're going to use the distributive property, just like I said earlier. 2 times 3x gives me 6x. 2 times negative 6 or minus 6 gives me minus 12. And I get negative 4x plus 6x minus 12 equals negative 8. I have like terms here, negative 4x and positive 6x. I can combine those. Negative 4 plus 6 gives me 2. So if I have negative 4x's and positive 6x's and I combine them, I get 2x minus 12 equals negative 8. Well, if I want to get this x by itself, I have to get rid of this minus 12. To do that, I'm going to add 12 to both sides. I get 2x equals 4. And to get rid of that 2, to undo the multiplication, I'm going to divide. And I get x equals 2. Now, we're not done. Okay? Because remember, I need a full coordinate. This is just half my coordinate. This is just the x. I still have to solve for what? Good, I need to solve for y. So, that means if I know that x is 2, I need to check and plug in 2 for x in this equation, and then I need to do it in the second equation as well. Why do I have to do that? Because again, if I made a mistake in my calculations, if I get x equals 2, it might work here, and I can solve for y, but it might not work here. I might not get the same y value. Okay? If that happens, I did something wrong and I have to go back and check my work. Maybe I distributed wrong. Maybe I added like terms incorrectly. I need to go back and check, okay, step by step. So we're going to substitute x equals 2 into the first equation. First equation was y equals 3x minus 6, okay? So if I plug in 2 for x, instead of 3x minus 6, I'm going to get 3 times 2 minus 6, because x is 2. So 3 times 2 is 6. 6 minus 6 is 0. Okay? You should have gotten 0 for y in the first equation. Now let's see what we get in the second equation. The second equation, if I plug it in, I had negative 4 times x plus 2y equals negative 8. Well, if x equals 2, negative 4 times 2 plus 2 times, we think y is 0, so let's plug that in. Negative 4 times 2 gives me negative 8, plus 2 times 0, which is 0. Negative 8 plus 0 equals negative 8. I get a true mathematical statement, which means that this point of 2, 0 has to be my solution. Okay? It works for both equations. It worked for the first one, and it worked for the second one. Okay, so this has to be the one point that they intersect at. So, how do we do this? First, when we're substituting, first step you're going to do is you're going to solve one of the equations for a variable. Okay? You might want to isolate x, it might be easier. You might want to isolate y, it might be easier. Maybe if both equations have a 2y, you might want to isolate the 2y. Okay? Just depends on what you're given. Step 2, after you solve for one of the equations for a variable, you want to substitute the expression that you got in step 1 into the other equation for whatever you're going to substitute for. Okay? In the last equation, we isolated y. That was our step 1. And then we took the expression that y was equal to and plugged it in to the second equation. Okay, that was our step 2. Once you do that, you're going to solve the new equation because everything should have the same variable now. Okay, everything should either be in terms of x or everything should be in terms of y. Once you solve the new equation, you're going to substitute the value that you found in step 3. So let's say everything was in terms of x. You're going to solve for x, and then you're going to plug in that x value into both equations to figure out what y is. Okay? And then you're going to check and make sure that that solution of x and y works for both equations. Okay? So in the last problem, we found out that x was 2. Once we substituted 2 in to both of the equations, we figured out that y was 0. And we checked that point in both equations to make sure that we did everything correctly. Let's try another example. It says solve the following system of equations using the substitution method. Here are my two equations. Okay, this one should be just as simple as the other one. I'm going to give you, realistically in the video, I'm going to give you about 10 seconds. Pause this video, take your time, solve it. If you need to go back, and hopefully you took notes on the last slide that I did where I worked out the problem. Look at the notes, compare them, try to figure this out on your own, okay? I'm going to give you 10 seconds on my time. Pause the video, solve it, and then check your work. Okay, so we already have y by itself, right? So since y is by itself, anywhere that I see a y in the second equation, I get to plug in 2x minus 5. Because this is saying that y is the same thing as 2x minus 5. And since the y in equation 1 has the same value as the y in equation 2, I'm going to substitute 2x minus 5 in for this y. It's going to look like this. I take the 8x minus 4y equals 20, and I remove the y, and I insert 2x minus 5. So this now becomes 8x minus 4 times, in parentheses, because remember, this entire thing represents y, so I'm going to quadruple both the 2x and the minus 5, equals 20. Okay, so I replace the y with 2x minus 5, and I have this new equation. What do I do next? Next, I'm going to solve for x. Everything's in terms of x. I got rid of the y. When you have one variable, you can solve the equation. So we're going to do that. We distribute. I multiply negative 4 times 2. I get negative 8. Negative 4 times negative 5 gives me positive 20. And I now have the equation 8x minus 8x plus 20 equals 20. What's going to happen here? Well, 8x minus 8x gives me 0, and 20 equals 20. Who can remember what happens when I have something like 20 equals 20? This is what kind of statement? It's a true statement. So if I have a true statement, what does that mean in terms of my solutions? What does that mean in terms of my graph? Well, if I have a true statement, that means that I have infinite solutions, right? So just as this says, when you get a result like this one on the previous slide, and it says a true statement, okay, and all my variables canceled out, this indicates that the two equations actually represent the same line, which means we have infinite solutions. Okay, you can read this to yourselves if you'd like to, but I just broke it down. You have infinite solutions when your variables cancel out and you're left with a true statement. We talked about this in the last lesson. So, if you can solve for the variables, meaning the variables don't cancel out, you'll have one solution. So in that first example, I guess the first two examples I did, the one with the internet and the one right after it, we found an x and a y value, okay? In those cases, we had one solution. We had one point that those two lines intersected at, okay? That's the only point that those two lines will intersect at. If the variables cancel out and you're left with a true statement like we did in the last slide, okay, or the last problem we did, it wasn't the last slide. If it's a true statement and the variables cancel out, you have infinite solutions, okay? That means every single point that's in the first equation that works is going to work in the second equation. And finally, if your variables cancel out and you're left with a false statement, for example, if, let's say, hypothetically, I ended up with -5 equals 17. That's a false statement. In that case, the variables canceled out and I was left with -5 equals 17, which is a false statement. Now I have no solution, okay? They're parallel lines. They're never going to meet. They have nothing in common, okay? That does happen with systems of equations sometimes. You have no point where x and y can be the same. So let's try another example, okay? It says solve the following system of equations using the substitution method. I have the equation 3x minus y equals 4 and 6x minus 2y equals 4. Now again, I'm going to give you guys 10 seconds of my time from the video. Pause it, solve this on your own, and then we're going to walk through it, okay? So go ahead. All right, so what did you guys notice that you could isolate? Maybe you tried to isolate y. Maybe you decided, hey, I can double this 3x and get a 6x here. But remember, if I double this, I have to double the y and the 4. There's a bunch of different ways you could have done this. In this case, we decided that we were going to get y by itself. Easiest way. Since y is already technically kind of a loner, has no coefficient except for 1, we're going to get y by itself. It's the easiest way to do it. Subtract 3x from both sides. I get -y equals -3x plus 4. Now I'm going to multiply everything by -1. I get y equals 3x. Instead of +4, it becomes -4 because -1 times +4 gives me a -4. So now I see that anywhere that I see a y in the second equation, I can plug in 3x minus 4, okay? Because y is the same thing as 3x minus 4. If they mean the same thing, I can plug in the 3x minus 4. So I'm going to substitute for the second equation. Second equation says 6x minus 2y equals 4. And since y is the same thing as 3x minus 4, I'm going to remove this y, and I'm going to substitute 3x minus 4 in its place, which means I'm going to double the 3x minus 4. So this is my new equation. I'm going to solve it because everything's in terms of x, which means I'm going to distribute. In this case, remember there's a -2 in front of it, or sorry, there's a minus in front of the 2. So that makes this a -2 that I'm distributing. -2 or -2 times the 3x gives me -6x, and then a -2 times a -4 gives me a +8, so it becomes +8. So I get 6x minus 6x plus 8 equals 4. What do you think's about to happen here? Yep. My variables cancel out. 6x minus 6x is 0. And I'm left with 8 equals 4. What do I know about 8 equals 4? Is that true? No. It's a false statement, right? So since it's a false statement, that means, that's right, that means no solution. There is no solution to this system. You can read all this if you want to. It's basically a long way of saying the lines are parallel, there's no solution, okay? We call this an inconsistent system, okay? It means that there's no solution. This is all you really need to know. It's a very technical term. I don't really care if you know this or not. This isn't that important. This is the most important part of what I just showed you in this slide. Okay, there's no solution. We were left with a false statement. Well, that's it. Next time, we're going to talk about the elimination method or the addition method. We're not going to talk about that today. I'm going to give you a worksheet to work on. You're going to work on that. So, thank you, and we'll get back to this next time.